Hello everyone, welcome to the seventh lecture of the series of this particular unit feedback amplifier, and today we are going to discuss about the effect of negative feedback on the performance of amplifier. And if you remember, we have already discussed in the first lecture of this particular series that how the negative feedback impacts the performance and operation of the amplifier. And today we are just going to uh, get into the detail version of that, and we'll try to understand that how we can consider the different design consideration for designing the amplifier, and how we can make the negative feedback more advantageous for us. So the outlines of today's discussion will be, we will be discussing about the effect of negative feedback on the different performance parameters of gain, bandwidth, noise and distortion of the amplifier. We'll discuss about the outcome and also the related questions with this particular topic. This is the first parameter that we are going to discuss. It is the gain of the amplifier. Now, if you remember that we have already derived a small equation of gain of negative feedback amplifier, and this negative feedback gain of the amplifier relates with the open loop gain by this particular equation, A upon 1 plus A beta. Now, we have already seen that this feedback gain is always going to be less than or equal to the open loop gain of the amplifier. And on which factor it depends? It depends on the factor of beta. So in practical consideration, in practical condition, we can say that AF is always going to be decreased. AF is always going to be less than the A. Why? Because the beta is definitely will have some value, and we can easily say that the AF is going to be lesser than the value of the A. So the first impact which negative feedback leaves on the performance of the amplifier is that it decreases the gain of the amplifier. Now, if we say that it decreases the gain of the amplifier, then how it stabilizes the gain by decreasing the value of the gain, and how we can say that the negative feedback is going to be advantageous for us in terms of stability of the gain, that we are going to discuss. Now, if you consider this possibility of lack in stability, it comes from the three main sources. First is aging, second is temperature, and third is the replacement. Now, aging is when we are using the electronic component or any component for the longer period of time, then it is very obvious that after certain time, the performance of that particular component is not going to be similar. So, as we also in day-to-day life, we let us consider an example of a lab, that if you experiment about the diode's VI characteristic. So if you purchase a new diode and see the VI characteristic, it gives you the a lot better value, or it can give you the ideal value of the forward and reverse bias curves. But if you same diode, if it is used after 3 years or 4 years or 5 years of time, then the characteristics is never going to be the same. So the aging definitely affects the performance of the electronic component. Temperature, obviously, because all the threshold value and current and voltage values are entirely depends on the variation on the temperature, because temperature is directly or indirectly related with the performance of the different performance parameter of the components. So temperature is the next factor that affects the stability of the electronic component, and so is the amplifier. Now, third is the replacement. If for any reason, if you are replacing the amplifier or any other electronic component in the circuitry, then definitely the performance again will never be similar as it has been performing for you for the years or for the days which you have been using the component. So these are the three basic the basic possibilities where we see that the stability lacks. And how we can find the possible solution? if we can somehow design the amplifier in such a way that the sensitivity gets reduced. When I use the sensitivity term, it means that the sensitivity of the amplifier to the changes. What changes? The aging, the temperature, the replacement of the components. So if somehow if you able to decrease the sensitivity term, or if you increase the desensitivity, that is the 1 plus a beta parameter d, which we have already defined in previous lectures as well. So today we will discuss about the what desensitivity really means, and how the desensitivity helps us in stabilizing the gain of the amplifier when we apply the negative feedback. So reduction in sensitivity. Second is making gain independent of the transistor parameters. So this is very important. If you make the gain independent of the transistor parameters, then also we can have the possible solution of the stability of the gain. So the stabilization of the gain or desensitivity of the transfer amplification will give us the possible solution of the stabilizing the gain of the amplifier, or we can say that effect of negative feedback has the stability of gain, and how we will see. So sensitivity can be defined as fractional change in amplification with feedback upon fractional change in amplification without feedback. So if you able to control the sensitivity factor, you will definitely be able to control the stability of the amplifier's gain. Now, as we know that AF is A upon 1 plus A beta, where A is the gain without feedback, AF is the gain with feedback, and beta is nothing but the feedback factor. Now, if we want to observe the fractional change in the amplification and without the amplification, we definitely have to monitor the change with respect to the gain A. So here I am differentiating the above equation, that is the equation number 1 with respect to A, and this leads to me to this equation. And finally we can define this equation. Why we are going for this particular value? Because we want to see the fractional change in amplification with feedback to the fractional change in amplification without feedback. So it is very important then what changes that has been occurred in the negative feedback amplifier with respect to the original value of the gain. So you see, DAF upon AF is going to give me the correct measure that what was the previous value of the gain with feedback, and what is the change, that is that small change, that is DAF. And similarly, what is the DA upon A will give me? DA upon A will give me what is the change in the open loop gain of the amplifier to the original value of the gain. So these factors are very important, and how we can we can analyze that if we divide this particular equation by AF. So if you divide this particular equation by AF, this gives me, the left hand side gives me the change in the value of the AF with respect to the original value of the AF. Okay, and similarly, if I replace this value AF here in the right hand side from the first equation, that certainly gives me this value DA upon A after cancelling out this. So this DA upon A, what it means for me, it is the change, a small change in the value of the gain with respect to the original value of the gain when we do not consider the feedback. What is the equation? Sensitivity, fractional change in the amplification with feedback upon fractional change in the amplification without feedback. Now here we can see that this is the fractional change DAF upon AF here in this equation, which gives me the value of change, a small change or fractional change in the amplification factor with feedback upon fractional change in amplification without feedback, and it is nothing but it is equal to 1 upon 1 plus A beta. Now what 1 upon 1 plus A beta is? It is nothing but the sensitivity. So what 1 plus A beta defines for me? It defines for me the desensitivity. So if we consider a small example, let us say that if sensitivity is 0.1, let us say this factor is 0.1. So definitely the D is 10. then only we can say that this factor becomes 0.1. So it shows that the percentage change in the gain with feedback is 1/10 of the percentage change in gain without feedback. So the ultimate outcome is, or we can conclude that if we apply the negative feedback, then the gain, the variation in the gain or fractional change in the gain becomes quite small, smaller than the gain, than the fractional change in the gain without feedback. So if somehow in designing consideration or designing of the amplifier we can have the larger value of D, let us say if we design D as 100, I'm just keeping it as an example. So we can have the value of sensitivity as 0.01, so it becomes the 100th of the sensitivity term. So then that will become the more stable value of the fractional change with feedback as compared to without feedback. So ultimately we can say that negative feedback is going to give me the better value of the gain. It stabilizes the gain, and if we can design the better desensitized amplifier, then definitely the sensitivity is going to be decreased. And when I say that sensitivity is going to be decreased, it means that we are intentionally making the transistor free from those circumstantial things that can affect the gain of the amplifier or operation of the amplifier. So negative feedback stabilizes the gain. Now if we again consider this particular equation, that is AF equals to A upon 1 plus A beta, which is nothing but A upon D also, and if we somehow able to design the thing that A beta can be greater than equal to greater than 1, then we can ignore 1 in this particular equation. Then that certainly leads to me A upon A beta. If I cancel out A, then it gives me 1 upon beta. So what does equation 3 suggests? Equation 3 suggests that if somehow while designing the amplifier we can make the amplifier or the gain of the amplifier depend entirely on the feedback network. What is beta? Beta is the feedback factor, and where it comes from? It comes from the feedback network. So if feedback network is going to be purely resistive, if it is going to be purely stable, and if we somehow in the designing process we can make the gain of the amplifier, that is AF, with feedback made entirely depend on 1 upon beta, then definitely the gain is going to be stabilized. So these are the two important points. First, if we increase the desensitivity, it will decrease the sensitivity, and if we make the transistor design or transistor amplifier design so that if it can depend entirely on the value of the feedback factor or feedback network, then definitely we are going to have the better value of the gain and the stabilized value of the gain for longer period of time. Let us go and see that what the effect of negative feedback on the bandwidth of the amplifier is. Now I also discussed this particular gain bandwidth product a little bit in case of first lecture, and we have seen we have heard also that the gain bandwidth product is the very important performance parameter when designing the amplifier. And if you simulate the amplifier as well, you have to define the value of the gain bandwidth product as well. And gain versus bandwidth, which is the plot which is shown over here, also we'll discuss about this plot. But one thing is very sure, that gain bandwidth product is going to be constant. So if you increase the gain, you will have the lesser value of the bandwidth. If you increase the bandwidth, you will have the lesser value of the gain, vice versa. So this quantity actually designers, it gives the designers the idea that how to determine the maximum gain in the given particular frequency points, and vice versa. Okay, so if you see, this A defines me the gain when we have not applied the feedback, and this A dash defines me the gain when we have applied the feedback, and this x-axis gives me the value of the frequencies. So if you can see that if we do not apply the value of the if you do not apply the feedback, then we have this kind of frequency range which lies between f1 and f2. Okay, And if we decrease this value of the gain, if we decrease the value of the gain, the frequency band shifts from f1 to f1 dash on the left hand side, and it shifts from f2 to f2 dash on the right hand side. Now, from where this analysis comes from? It is very obvious. These points, this corner point, this is one corner point, and this is another corner point. What is this? These are the points which gives me the 0.707 of the original gain value. And what is 0.707 of the original gain value? That is a 3 dB point, 3 dB frequency, 3 dB point. 3 dB is the power point which gives me that if I design the amplifier in this particular range, that is, this is the lower 3 dB value to the higher 3 dB value. Okay, this is the lower limit and this is the higher limit. If I use deliberately this range, then I will have the better performance of the gain throughout this band of frequencies. Now, this is universally accepted that if we take those 2 points, or those points where we can have the power of the particular amplifier generally defines for the operational amplifier, half of the original power, that is just half of the original power, those points are known as the 3 dB points. And if we consider these 2 points, that is the corner points which I mentioned in this particular slide, then the performance on the amplifier will be smoother. Okay, now if we decrease this gain, obviously we will shift to the lower frequency points because we are decreasing the gain. So we shift to the lower frequency points, and similarly here since the higher limits, we will shift to the right hand side of the frequency. So what this ultimately gives to me, that if I decrease the gain, the bandwidth is going to be increased. So if we apply the negative feedback, the amplifier have the larger bandwidth which lies between this f1 dash to this f2 dash, as pictorially shown over here. So now this is going to be the band of frequency for which I will have the smoother performance of my amplifier, or gain will be going to be stabilized. So the next effect which we have seen is the negative feedback gives me the higher band of frequencies. It improves my bandwidth so that I can have the performance of the amplifier, that's the gain of the amplifier, to be constant, or stabilize over the wider band of frequencies. So this is the second outcome. Now, distortion and noise as amplifier is, as previously discussed, these are the new not new topics, and if you apply the same reasoning, if amplifier is designed in such a way that its working becomes free from the reactive elements, then unwanted frequency or phase distortion could be avoided. Now, if as I already discussed, if you make the feedback network such that if it is going to be entirely dependent on the resistive values, then if you don't apply the reactive components like inductor or capacitor, there is no change with respect to time. If there is no change with respect to time, your linearity will increase. If your linearity will increase, if the non-linearity is going to be decreased, the distortion is definitely going to be decreased. Now, similar analysis we can have for the noise as well. If we increase the desensitivity of the gain, so when I desensitize the gain, I also desensitize the amplifier to have the noise values, because noise is directly related, or directly indirectly both, it is related to the voltage values. And we are not discussing the noise in detail, but you can say that since the current and voltage value is going to be stabilized, the gain is going to be stabilized, the noise is also going to be stabilized, because we are increasing desensitivity. So ultimately we are having the lesser noise values when we apply the negative feedback. And what are the outcomes of today's lecture? We have seen that if we apply the negative feedback, the gain is going to be stabilized, and we can have the better value of desensitivity for that, and we can have the good performance of the amplifier, good performance of the gain over the wider band of frequencies, so bandwidth is going to be decreased, or we have the better performance over the wider band of the frequencies. This can also be said. Similarly, noise and distortion is going to be decreased as well. So what can be the questions we can expect from this particular lecture is that you can be asked about the impact of the negative feedback on amplifiers performance and operation. You can be asked to list out the advantages of the negative feedback, how negative feedback helps in improving the performance of the amplifier. This can also be the question that can be asked. So this is how we can analyze the feedback amplifier. So if you are having any doubts, you can ask in the comments as well. And I strongly recommend that go through the lecture number 1 to lecture number 7 in order to completely understand that what we have discussed from the basic theory of the amplifiers operation, the category of the amplifier, how we can define the different configurations of the amplifier, what are the sampling and mixing networks, and how those sampling and mixing networks help us to determine the voltage shunt, voltage series, current shunt, current series configurations. Then how the impact of the negative feedback is going to be on the performance of the amplifier. So all these discussions we have covered in the 7 lectures, and I will prepare some lectures on the numerical topics of the feedback amplifier as well. Let us say in 1-2 lecture we will cover that as well. And today we can say that we have wind up the theory portion of this particular feedback amplifier unit. Thanks for watching and stay tuned for the more updates.